Hello engineers, welcome back. In the previous video, we started coding the binary search tree in C++. We coded the search operation, we coded the insert and display. In this video, we're going to continue the same. We will implement the remove method. Okay, I hope you're ready. Let's get started. So if you remember the video on binary search trees theory, we discussed the remove method where we have to handle three cases. The first case is the leaf node. The second case is the node having one child, and the third case is the node having two children, right? So if it is a leaf node, we will directly remove it. There is no impact on the structure of the binary search tree. If it is one child, we will retain that child and connect it to the parent. And if it is two children, we will implement either of these strategies. First, we will find the rightmost node in the left subtree and use that to replace the node to be removed, and then remove the rightmost node. Okay, so we will implement one of them, but I will give you the code for both of them in GitHub. Okay, so let's see. Let's go to VS Code. So we stopped here in the previous video. Now let's implement the remove method. Remove will take in a value. This is what we need to remove, and then let's do a root check. Tree is empty. Return. Otherwise, let's start building our first case where the given node is a leaf node, right? So before that, we need to first find the node. So considering all the things that we need to do here, let's implement a helper method which will get us the node and its parent. For example, if we want to remove the node 90 and we need to retain or let's say we are removing 95, it has one child, we need to retain this 93. So what do we need to do? We need to connect 93 to 90, right? So we need to find 95 as well as 90 so that we can do both operations, right? So let's implement a common method where we can get both the node and the parent. So we can use the concept of pair here. So we can say pair node star, and let's call them nodes, and let's call our method as get node and parent, and we will pass in our value. Okay, so because we are using pair, we need to include utility. Okay, I've already done that. So let's implement our method. So we can use pair node star comma node star, and now we can implement our method value. So what do we need? This is like a search. First, getting a node is a search, right? We can use the concept of binary search again, right? We compare the given value with our root. If it is greater, we will go to the right. If it is lesser, we'll go to the left, right? So let's implement the same thing. Let's start with the current pointer at root, and while current not equal to null ptr, we will continue. So how do we continue? If given value is less than current value, then we go left. Current will become current arrow left, right? Else, if value is greater than current arrow value, then what do? We can move current to right, current arrow right. Okay, and the third case is else, where we actually find the node. At this point of time, we can return the node and parent, right? So let's make a pair, make pair, and we will return parent and current. Okay, but we have not declared the parent. Let's implement the parent logic as well. So parent will start at null pointer because there is no parent to the root, and at every step we will just update the parent. Parent equal to current, parent equal to current, right? So after this, we can simply return this pair. Okay, so after completing this loop, if the node is not found, then we can return null ptr null ptr. If the given value is not part of the tree completely, then we can return null ptr null ptr, right? So this will be our logic to get parent and node. So we have these here. Let's extract them. So let's call it parent equal to nodes dot first, and let's call it node to be removed equal to nodes dot second. So I'm just extracting the first and second values from the pair to new variables, right? Here we can do a check. If node to be removed equal to null ptr, then we can say node not found and return. Okay, otherwise we have found our node and our parent. Now we can start with our first case. First case is leaf node. If it is a leaf node, we can directly remove it. No need to do anything else, right? So let's check. If node to be removed arrow left equal to null ptr, there is no left child, and node to be removed arrow right equal to null ptr, which means that it is a leaf node, then we can simply say delete node to be removed, right? But before that, let's also remove the connection to the parent. So to remove the connection to the parent, we need to check if parent arrow left equal to node to be removed. If it is the left child of the parent, then we can say parent arrow left equal to null ptr, and we will repeat the same for right. Else parent arrow right. If parent arrow right equal to node to be removed, then parent arrow right will be null ptr. Okay, so we have removed the connection. Okay, so there is also a case where parent is null, right? So if we are removing the root node directly, we need to also handle that case. So what can we say? If parent equal to null ptr, which means we are removing the root node, then nothing to do, directly delete the node and we can return from here, because if parent itself is a leaf node, there is nothing else to do. We'll delete it and return, and we will actually make our parent root as null. We can make our root as null. Okay, so let's test this. Let's remove our leaf node. Let's remove 110. And let's do a display again. And let's call our display method. Okay, so we are testing the first case. Okay, so there were some syntax issues, I fixed them, but now our code is working fine. So after removing 110, this is how our tree is looking like: 100, 90, 85, 90, 90, 95, 93, 100, 90, 80, 95, 93. Oh, 85, 95, 93. Okay, no problem. Now let's talk about case 2. Else if node to be removed, it has one child, node to be removed arrow left equal to null ptr, or node to be removed arrow right equal to null ptr, right? So either one child is there, so we need to retain that child. So let's get that child out first. Child. So if node to be removed arrow left is not equal to null ptr, then child equal to node to be removed arrow left. We are extracting the left child. We will do the same thing for right child as well. Else if node to be removed right is null ptr is not null ptr, then we will extract the right child, right? So now what we need to do, we need to connect it to the parent, right? So for parent, again we need to check whether the node to be removed was on the left side or on the right side. So if parent arrow left equal to node to be removed, then parent arrow left will carry the child. Otherwise, else if parent arrow right equal to node to be removed, then parent arrow right will become the child. So we have retained the child. Now we can safely remove the node. Okay, so let's test this. So let's remove 95 so that this left child will be retained and attached to 90, right? So let me repeat this. Let's remove 95. Okay, after removing 95, we have 100, 90, 85, 93. We have 4 nodes left, right? So our case 2 is working fine. Now let's talk about the third case where there are 2 children. This is case 3, node with 2 children. So this was case 2. Case 2, node with 1 child. We retained the child and attached it to the parent. Now we will discuss case 3, node with 2 children. So what was our strategy? Our strategy is, so for example, if we are removing 90, who can take the place of 90, because 90 is having 2 children. So we will use the first strategy, rightmost node in the left subtree. So we will go to the left subtree and find the rightmost node, which is 85, and replace it with 85, and finally remove 85. If 85 is already having any child, then we will attach it to 85's parent. Okay, so that will be our algorithm. So let's implement this. First, let's find the rightmost node in the left subtree. So for that, let's create a new pointer, rightmost node, where we will start it at node to be removed arrow left, right? So this is where we'll start our search. So from 90's point of view, we will go left side, and within this tree, we will find the rightmost node, right? So let's do that. So while rightmost node not equal to null ptr, we will keep going. Rightmost node will keep going to its right. Okay. So after this loop, we will find our rightmost node in the left subtree. So we have started in the left subtree and we are going right. So we will find the rightmost node. Okay. Along with this, let's also keep track of the parent. Rightmost node parent equal to node to be removed. So what is this parent? So when we are here from 90's point of view, we started our search for the rightmost node in the left subtree with 80. And who is the parent of 80? 90. And when we go to 85, who will be the parent of 85? 80. So we will keep a track of 80 so that when we reach the end, if this fellow has any child, we can attach it to the parent, right? So as we go through the loop, let's also update the parent. Rightmost node parent will now become rightmost node. Okay, we are simply updating the parent as we go down the levels. So now we have node to be removed, we have the rightmost node, we also have the rightmost parent. So what will be our steps? First step is, we found 85, right? So let's replace the value of 85 into the node to be removed. So node to be removed value is equal to rightmost node value. So we have done the change. Now we can delete the rightmost node. Okay, but before we delete, we need to do a check on the child. So let's get the child out. Child will be rightmost node arrow left. Why left? Because 85 can have left child or right child, right? But if it is having a right child, then that fellow will become the rightmost node, right? If that fellow is the rightmost node, then that node will not have the right child anymore. Okay, it can only have the left child. So let's retain the left child. Now we will attach it to the parent. So we will quickly do a check whether it's on the left side or the right side. So if rightmost node parent arrow left equal to rightmost node, then rightmost node arrow left will carry the child. Else if rightmost node parent arrow right, if it's on the right side, then we will attach it to the right side. Rightmost node parent arrow right will carry the child. Okay, we are attaching to the parent. So here it is parent. Okay, so this is first step where we have replaced the value of the rightmost node to node to be removed. This is one step. Second step is check if there is a child, right? If there is a child, attach it to the parent. Now we can remove the rightmost node and return. Delete rightmost node and return. Okay, so these are our steps. So we can use the same logic for our second system as well. Leftmost node in the right subtree. So only thing that will change is this will become right, and instead of going to the right, we will be going to the left. Okay, and the remaining steps can be altered in the same way. Okay, so now let's test this. So how is our tree now? So we had this one, right? 100, 90, 85, 93. 100, 90, 85, 93. So let's remove the node 90, right? So we are removing the node 90, and for this we are going on the left side and finding the rightmost node. So 80 should take its place and the remaining tree should be the same. Okay. Okay, now after removing 90, our tree is looking like this: 100, 85, 93. So which is perfectly fine. So just a quick recap what we did here. So we found the rightmost node by going into the left tree. Okay, so once we go into the left tree, we keep going right. Okay, so one correction I made here: instead of going rightmost node not equal to null ptr, we need to do rightmost node arrow right equal to null ptr, because once we reach the end of the tree, there will be no right pointer, and it will give segmentation fault. Okay, so just one correction there. After that, we found the rightmost node, then whatever is the rightmost node's value, we put it in our node to be removed. So that step is done. After that, we are checking if there is any child. If there is a child, we are just attaching it to parent. If there is no child, there will be null pointer in this and parent will have null pointer. So this code will work just fine. After that, we are just removing the node. Okay, so these are our operations. Please try to code it yourself and see how they are working. It's a very interesting use case. And then you can also try to do the opposite side with the left most node from the right subtree and implement the same strategy. Okay, so the code is already available in GitHub. You can refer to the same if you have any doubts. Okay, so those are our operations. So far we have discussed all the operations. Now let's see what are the time complexities of these operations. Okay, so let's start with search. So in a typical binary tree, the search operation would take O of n, but in a binary search tree, the operation would be O of log n. Why? Because at every step, we are reducing the search space by half. So if we are at 100, and if you need to find 95, we only look at the left subtree. So the right subtree search space is removed altogether, right? So similarly, as we go down the levels, the search space is getting reduced by half. So this is O of log n operation. What about insert? Insert is also log n, because what are we doing for insert? Again, we are trying to find a space to add a node, and for finding the space, we are again doing the same binary search operation where we are looking for a node in half the tree at every level, right? So this is also log n. Display will be O of n because we are printing everything. Remove will also be O of log n. Why? Let's see. So what are we doing? First, we are trying to find the node, right? For finding the node, we are doing log n operation because we are splitting the tree into half to find the node. After that, all the operations are also log n, because if we are finding the rightmost node in the left subtree, we are going one level at a time and using only half the search space at each level, right? So there also it is log n, and overall complexity is also log n. Okay, so those are the time complexities. So finally, we have come to a conclusion and we have successfully implemented a binary search tree in C++. So if you have come this far, congratulations. If you have any doubts, definitely ask me. Thank you so much for watching. Please don't forget to like the video, bookmark the playlist, and don't forget to leave a comment if you have any questions or suggestions. Thank you so much for watching, guys. I will see you in the next one. Cheers.